reminder that the program itself, what we're trying to do through these webinars is sort of strengthen the community of engaged practitioners, policymakers, and researchers in the field, and overall try to kind of strengthen our understanding of the sources and behaviours of pollutants within river systems, and ensure we know how these pollutants are interacting and accumulating in the environment and what their impacts might be. What are the kind of ways we can support the policy and practice community with that science to kind of ensure that we get better water quality, basically. And so in the program, there's 5 main projects, large projects. And in the first half of 2024, we had webinars, update webinars from each of these projects. And then what we plan to do from January 2025 onwards then is here updates from each of those projects, but actually to kind of do some deep dives. So we'll have, rather than an overview of each project, we'll actually do some deep dives into particular components of the projects to kind of find out some of the detailed new science knowledge that's been developed from those projects. At the last webinar, so in November 2024, we heard from Professor Alison Dunn, and she presented on invasive non-native species and some of the critical issues around those, but also particularly alerted us to the fact that as freshwater researchers, when we're sampling in the environment, we may also be potentially a conduit for causing further kind of invasions, basically. And you know, the best way to sort of deal with this is prevention, rather than kind of dealing with it once things are in the system. So there's a QR code on the left-hand side of the screen called Biosecurity e-Training, and we just encourage you to go to that. And it's a really simple online e-training program where you can just work through some of the online materials and then do some questions and so on that. And that's, I think, really helpful. And we're currently working with UKRI to see whether we can make this a kind of mandatory, this training mandatory as part of people securing funding in freshwater projects, because we think it's so important. So just as a note, you can click on, or you can connect to that e-training there. Okay, so before we kick off with today's presentation, just a note then on upcoming presentations. So January the 20th at 12 noon, so a bit of a change of time. We have an update on the EcoMix project. February, we're just confirming the date, so we'll alert people to that for the MOT for Rivers update. But then March the 12th at 12 noon, we've got an update on quantum. So that's the kind of January, February, March webinars that are coming up. So that's just by way of overview and what's coming. So today we're really happy to have Dr. Barney Dobson here from Imperial College London, and there's been some really interesting work going on with some modelling that's been developed that actually could be really interesting and useful for us to kind of understand and look at attribution around water quality. So Barney's going to tell us all about that today. So Barney's currently an Imperial College research fellow, and we're delighted that you've given up some time today to present to us, Barney. So we're going to hand over to you. So I'll just stop sharing my slides and then hand over to you. As I say, just to remind everybody to as we go along, please put questions in the Q&A as we go along, and then we'll pick them up at the end. Over to you, Barney.
Sounds good. Thanks very much. Let's bring these up. What is this? So I don't can go over the logos. Looks like I'm sharing, so if I'm not, please interrupt. Yeah, thanks, Joseph. I'm Barney. I'm a research fellow, but most of what I'd be presenting is not work that I've done on the current position I'm in. It was work done on a postdoc with Anna Miech in the Water Systems Integration Research Group as part of the NERC Camellia project. The work I'm presenting today is from a wide range of people. I've put Xian and Liang in this middle bit because the results I'm showing are results they produce, but this work is based on actually a wide range of people over a 4-year period, or 5-year period, I should say. And it's the name of the software that we've created is called WSIMOD, which is a simulation tool that is a physically based dynamic tool, but is targeted towards systems level water planning and management. And hopefully by the end of this presentation, you will have an idea what it does and agree that something this or something like this is useful if we want to improve in-river water quality through water management. So something that we are often need to persuade people on, in my view, the more expertise you have, the harder it is to persuade someone about this, but the less expertise in a given infrastructure system they have, the easier it is to persuade someone, which is, does integration in the water cycle impact me? By integration in the context of modeling, I really mean joining up models that are not usually joined up. That's a kind of my definition of it. There's lots of definitions, but for my purposes, I do modeling, and so integration in the context of modeling is, are you joining up models that are typically simulated separately? And our often response is that people come from kind of expert domain modeling, and so they are often thinking, well, you know, I understand that integration might be important, but it's probably not important for me because the models I use help me answer all the questions that I care about. This is a really common attitude, and the view is really that any model that is not the models that they use is probably insufficiently detailed or tailored enough to the questions they're answering. And my response to them is typically, yes, you're probably right, but you also realize your system interacts with many other systems because it's part of the water cycle, and therefore the decisions you make can have knock-on. For a start, some evidence that that is the case. So I like to suggest that functioning infrastructure, by which I mean infrastructure, water infrastructure following the law, which despite what you read in the news is overwhelmingly what happens. Water companies do break the law. I'm not trying to say that they don't, but overwhelmingly they don't break the law. And overwhelmingly our infrastructure is operating as it was designed to do. Not in every case, but in most cases. However, as I'm sure everyone here will be incredibly aware, that just because our infrastructure is doing what it was supposed to do, we can still have really poor Water Framework Directive classifications, for example, indicating that our water quality in rivers is not sufficient, right? So we have this disconnect of that our infrastructure is doing what it's supposed to do, but the rivers do not look how we would like them to look. And the premise of a lot of our research over the last 5 years is that this is because infrastructure is designed and operated without sufficiently considering in-river conditions. I made this slide when sewer spills was in the news every single day, but I think it's still a good illustration, which is that forget about any complicated modeling, even the simple fact of dilution means, again, I hope based on the audience here that this shouldn't be too much of a stretch, but just the simple fact of dilution means that how your infrastructure behaves is only half the story, and what does your receiving water look like is the other half of that story. So you could have quite a small spill into a small river, or a big spill into a much bigger river, and even though this big spill might be breaking the law, because this river is so big, it might not be as much of an issue as a smaller spill, which is maybe not breaking the law into a smaller river, right? It's a simple dilution, right? It changes how the infrastructure impacts propagate in rivers. So this was at a time when we were discussing in the news, you know, potentially spending billions or hundreds of billions of pounds on fixing sewer spills. And my concern here is that if you don't think sufficiently about the river, you will risk spending insane amounts of money and potentially not even see water quality improve. That discussion seems to have matured a bit, I would say, so that's at least encouraging. If that didn't persuade you, I'll show you a map. This is the Thames Basin, where we have indicated in blue dots pumping station, in red dots, surface water abstraction pumping stations, in red dots wastewater treatment plants, the blue lines are rivers, and in grey is urban land use. And so when you view it in a map, it becomes really abundantly clear that kind of whatever you do anywhere in the water cycle, especially if you are moving large amounts of water around, you are likely to have knock-on impacts on other things. We are abstracting water just above of where we're discharging water. We're abstracting water that we have previously discharged. We are abstracting water that has run off urban surfaces. So we've got a very high level of, I would say, integration exists inside the water cycle. So and then just to kind of hammer that home, a nice example I like to give, which is, if you, again, just returning to dilution, if anyone's still not persuaded, take a river, it's got some amount of water in, say we abstract half the water in that river to put it in a reservoir, that leaves a certain amount downstream. Let's assume it's a day when there's a combined sewer overflow. So you've got some raw sewage in the river. Obviously raw sewage is not good to have in the river. So we could end up with a river that's, say, 50% polluted water. And then what we do in our reservoir will determine the dilution of that raw sewage. So if we abstracted a lot of water, we'd leave less in the river and have more concentrated sewage. And of course, if we abstracted less, then we could dilute the sewage. Hopefully all of this should feel quite trivial to you. It's just dilution, but it can have enormous impacts on what is the actual in-river water quality. And we found that even though we have a pretty good understanding of how the water cycle is joined up, most people are more or less agreed on the kind of textbook diagrams of what the water cycle looks like. This is one such diagram, it's not the only diagram. We model and regulate all of these systems in a very separate way. So we've got water resource management planning for the supply system, drainage wastewater planning for the urban and wastewater, urban drainage and wastewater systems, and then rivers and groundwater kind of come under the Environment Agency in Water Framework Directive. That's not to say that these people don't all talk to each other. Of course they do, but overwhelmingly we find that their models are completely separate. So you might say, if you're a water supply modeler, well, it's still okay, because really the one thing I care about is, like, I don't know, days of hosepipe bans. And so I can model days of hosepipe bans really accurately if I only consider what's within this blue box. Even if you take that approach, which we have lots of evidence to show that that's a dangerous approach to take, I won't go into that because it's incredibly technical, but even if you support an approach like that, which is that your model, your subsystem is, you have the models to deal with the questions you care about, increasingly that's not going to be valid, because increasingly we're considering options that just are inherently spanning multiple systems. Wastewater reuse is one such example, where we're in some way repurposing wastewater to make it suitable for the supply system or augment it in some way. And these same dilution diagrams, of course, you can make it a lot more complicated than this, but it still works in a simple mass dilution context. Is you could say, well, if you have some effluent going into the river and you have some water in the river, and if you direct that effluent to your water supply, even though you've got less water in your river, provided there's enough water, effluent is quite dirty, right? It's not as clean as clean water. We treat it and it gets cleaner, but it's still a lot more dirty than clean river water. So you could find that wastewater reuse could improve your water quality, because you're directing that effluent away from the river, which would be a nice positive impact of wastewater reuse. On the flip side, if you had a sewer overflow in a combined system and there was lots of water going through your system, directing that treated effluent away from the river would actually concentrate the raw sewage in the water. And obviously raw sewage is a lot more polluting than treated effluent. So, you know, I'm not trying to tell you that wastewater reuse is good or bad here. Obviously, it feels like something we should be exploring more. What I'm trying to raise to you is that when we move large amounts of water around, we have the potential to improve or worsen in-river water quality or have other knock-on impacts that may not be necessarily incredibly complicated. All these mass diagrams hopefully are reasonably straightforward to follow, but you need some kind of model to help you figure out what these might be and help you assess the local and temporal elements of these questions. So we found that there wasn't really any modeling software that was sufficient to answer these kinds of questions. As I showed you, these kinds of questions, at least in a first attempt, can be answered in quite a simple way with just even mass diagrams. So we decided to create a software called WSIMOD, which is designed to do just this, right? So to provide parsimonious, but broadly covering parsimonious simulations that broadly cover water quality and quantity across the entire water cycle, right? So urban and rural systems, everything you need to determine what's in your water. It's a open source Python package. This is what it looks like in a very kind of simplistic. This is one of our kind of demonstrator models. It's node and arc based, and each node is a model, right? So you can see here these pink nodes here. These are the hydrological catchments. We've got 4 hydrological catchment models. Each hydrological catchment model is a node that puts water into other nodes, right? So these two join together. You can make an abstraction from the river, send it to a reservoir, and so forth, right? And each node here is some kind of model, and the links that join them are arcs, and these arcs convey water quality and quantity information. And that's how the simulation happens, right? Through interactions between nodes via arcs. This is a more kind of textbook arrangement, if you prefer your kind of textbook diagram type things, but a key element of WSIMOD is that it's highly customizable. So even if you feel you have a system that doesn't look like a textbook, which in my experience is most systems do not look like textbooks, you can customize this very easily. I'll show you with some examples some of the more kind of unusual kinds of setups you can accommodate with WSIMOD. Okay, so what is WSIMOD? When we talk about WSIMOD, we're a bit clumsy and we talk actually about 2 different things. We've got the model setup and then the model itself. Now, I don't know if you can see this top bar. Hopefully you can't, but it doesn't really matter. So the model WSIMOD model setup includes data acquisition from open source available data sets around England and Wales. We haven't got it set up for Scotland yet because their data sharing is not following like the same kind of formats as the EA, and then pre-processing those open data sets into the parameters of a WSIMOD model. It uses loads and loads of data sets, and therefore it's not quite fully automated, but it will be soon. We hope to have a API that lets you automatically set up a model anywhere in England and Wales. But this is currently closed source because it's not fully automated. We know that if we made this open source, we would get hundreds of emails or hundreds of GitHub issues about people saying, why is it not working? So our hope is to package this in an API, and then it will be fully automated by then. So we use openly available data sets to parameterize the model, and the model consists of all these different nodes and arcs, right? So these 3 bottom boxes are what is the publicly available WSIMOD software, which is a kind of parsimonious Python representation of all the different parts of the water cycle. There's more than this, I just couldn't fit them on the slide. And each of these would be like a node. You could have multiple reservoirs, multiple treatment plants, multiple rivers, etc. And these nodes can all communicate with each other. And I think a unique thing about WSIMOD is they obviously communicate in like the obvious ways. So like a urban drainage discharges to a sewer, discharges to a river. So you have all of those kinds of classic interactions, I would say. but you can actually connect anything to anything else. So if you want to accommodate something like wastewater reuse, for example, which is not as commonly facilitated in modeling softwares, it's simply just joining up the wastewater treatment plant with, maybe your supply network, or maybe with a pumping station if you're doing some kind of offsetting. So it's very easy to join things up and capture integrated representations of things that are often quite difficult to capture. The final thing that we give a user control over is called orchestration, which is probably too technical to go into in the main presentation. For anyone who is a modeler, orchestration is really the order of operations within a time step, which doesn't seem like it would be something you would want to change, but if you have lots of different parts of the water cycle integrated all together, there are examples I can give where the only way to capture certain effects are by changing the orchestration. I won't talk about that too much, unless people have questions. WSIMOD is, as I said, open source package and well documented. The idea is that anyone can become reasonably proficient in it through the online documentation. Of course, it's easier to learn Excel, but we think that this is easier to learn than most kind of other research software out there, because we've put a lot of effort into our documentation. And the software package itself has been peer reviewed in this thing called Journal of Open Source Software. So research software engineers have looked through the actual code as well to review it. It's featured in many peer review articles and many in practice applications, which I can show you on a timeline here. So we've got down the bottom our papers, and up top our impact studies is what we've called them, but this is essentially people contracting us to set up models for areas and using them for real world applications and questions, which is really exciting. It's exciting to have both the papers and the real world applications as well. I'll just give you a kind of couple of case studies here. One is to just demonstrate that it works and the kind of breadth of things that you can capture, and the other is to illustrate what you might use it for. So the first case study I'll show you, this should be relatively quick, is in Luton. We picked Luton for a variety of reasons. Luton is if you look, this is the urban coverage within the Luton catchment, and it's probably, I don't know, I haven't reviewed it, but I would imagine must be one of the most urbanized water bodies that's out there. It's got very large urban coverage. It's quite well gauged. It's got quite complicated groundwater. It's got a treatment plant. So for us, it's a really nice, small case study because it's just one catchment. It's in headwaters, but it captures and has lots of elements of the types of things that we think WSIMOD is useful for. And so this is kind of where we picked this study. This study was actually set up to demonstrate our groundwater behavior. So the groundwater is really important in this part of the country, and really important and quite complicated in that there's lots of lateral flows between aquifers. And we wanted to demonstrate that it is possible to get somewhat reasonable groundwater behavior even using our parsimonious simulation approach. I've said parsimonious a few times now, I realize. If you want a very quick mental comparison, I would say if you're familiar with lumped hydrology, so that's when you conceptualize a hydrological catchment to a single catchment and you parameterize that whole catchment and get simulations, it's that kind of thinking, but across the whole water cycle. So quite aggregated representations, and we're doing the same for groundwater as well. And we were able to show that you get somewhat reasonable flow and water quality calculations. If anyone's a hydrologist in the audience, they might be thinking this Nash Sutcliffe 0.6 is not actually very good on flow, but this is an uncalibrated model. So whereas typically we would calibrate hydrological models, in WSIMOD we don't. That would take me too long to explain why, but I'm happy to answer a question on it if you're interested. So it's quite good performance for an uncalibrated model. And we do water quality simulations and also groundwater simulations. So of course, again, the groundwater leaves quite a bit to be desired, but our point was at least we were capturing the kind of temporal dynamics of the groundwater behavior, even if aggregating at such a coarse scale, which was nice. So this is a kind of proof of concept study, and it's like a small system, so we use it for quite a lot of kind of experimentation with WSIMOD. A big case study is one we've done in the Upper Lee, which actually contains Luton, which we did for the Greater London Authority. This just gives you a range of the kind of scale of the WSIMOD model you can set up. It's got lots of different urban areas, lots of hydrological catchments, lots of treatment plants, water supply system, lots of different farming and crop cover. So we've got lots of different crop models in WSIMOD, wastewater catchment. I'm trying to remind myself. Gardening, or like loads of different things. In our view, everything you need to capture the terrestrial water cycle, at least at large scales. So this is kind of a rendering of the data that goes into that model. Also, the Lee is, if anyone's tried to model the River Lee before it flows into the Thames, or it flows into the tidal Thames, I should say. It's an absolute nightmare. It's got really weird groundwater. It's got rivers that you can see the river network here, right? You've got rivers like splitting and rejoining, and it's a real mess. So our view was kind of, if we can set up WSIMOD to do well in the River Lee, we can probably do it in anywhere in the UK. And that's exactly what we did for this project for the Greater London Authority. Why am I showing you this model? Well, to give you an idea of these integrated models, but also to show you why. This is my last kind of content slide, and then there's just one more, which is a summary. There's quite a lot of information on this slide, so I'm just going to tell you exactly what I want you to look at. So Greater London Authority wanted us to do lots and lots of different things with this model. I'm just going to show you one thing that I think illustrates why WSIMOD can be really useful. So one of the things that they wanted to look at was I can't remember how much it was going to cost, but hundreds of millions of pounds being spent on wastewater treatment plant phosphate removal upstream of these rivers. So big investment project as part of WINEP commitments, lots and lots of money on phosphate removal at the treatment plants. And it was clearly needed because the phosphate level in the Lee was it depends where you look, but is poor, right? It's not poor or failing, right? So it's not doing well on phosphate. Phosphate is a really common problem in Water Framework Directive throughout England, and maybe Wales. Actually, I'm not sure. So it was clearly they're targeting the right thing by increasing phosphate removal at the treatment plants. And we ran this scenario through our simulation, and we found that when you improve the phosphate removal at the treatment plants, you would indeed improve phosphate levels in the river, and they would go from a failing classification to a poor classification, which people were a bit kind of confused and upset about, because they're like, you don't understand how much money we're spending on all of this. Like, why are we not getting to good or high, right? Because anything that's not, as I'm sure people are aware, anything that's not good or high is really needs improvement. And so we thought, we're like, maybe our model is not working, but we looked into our model, and because everything is physically represented in WSIMOD, it lets you trace where pollution has come from and attribute pollution on a given day to its different sources. And what we're essentially able to see is that indeed these wastewater treatment plant improvements do massively alleviate phosphate from the FAL system, from the wastewater treatment plants. In fact, it was removing more than 90% of the phosphate from the sewage. So they were working, they were doing a really good job, and they were actually removing loads of phosphate from the sewage and from the river. To go from a failing classification to a poor classification, you would really have to half the amount of phosphate in your river. So they are actually having a really positive and significant impact. But it was still a poor classification, and because WSIMOD is physically based and you can do attribution with it, we were able to see that, well, 50% of the phosphate in the river was coming from fertilizer upstream, from farming. And so really, if you only target the wastewater system, you will never be able to go beyond a poor classification in this river. And for us, this was a really kind of nice study to highlight the importance of doing integrated thinking. It's not a complicated finding. It's quite easy to convey to people that 50% of the phosphate is coming from the sewage system and 50% is coming from farming. That's not very complicated. And it's kind of obvious when you say, well, all of a sudden when you add these things together, you're not going to be able to do better than poor. But you know, the thing of having a model is it forces you to look in these places and realize these things and gives you evidence to support decision making around it. So for us, this was a really nice kind of casebook study of why WSIMOD can be useful. There's lots and lots of other findings with this study which people can ask about if they're interested. So final slide, why do we think WSIMOD is useful? Well, as I just showed you, pollution attribution is something that we really care about. Representing the entire terrestrial water cycle is really good, obviously, to alleviate boundary condition errors, which is the kind of reason we did it in the first place, because we realized that not joining things up forces boundary condition errors. But something we didn't anticipate at the start, but has become actually maybe even more important, is that when you represent the entire physical water cycle, you represent a large number of stakeholders and their interests. And that actually means that people can be included in a common model that represents everyone, which is really, really useful for real world applications. So it lets you understand the system and the stakeholders in the system, and it lets you do all the other kinds of things you would do with simulation models. So testing scenarios, testing options, adaptive planning, all the optimization, all these kinds of things we like to do when we have models that we trust. And we've also tested in the upper Lee license reform as well, which I won't talk about now, but if people are interested, they can ask. Okay, I can't remember how long I had, but I will probably cut it now so that people have the opportunity to ask questions.